Okay, hello again everybody. We are going to continue tonight with TensorFlow Mahalanobis Distance. Last week we managed to actually implement it correctly. This week we're going to try to properly do that. Sorry, not properly implement it. We're going to try to implement it entirely in TensorFlow. We'll see how that goes. Excellent. Okay. This is a wiki page. Again, Wikipedia is asking for your donations. I don't have a particular stake in that. Close. Alright, again, this is Mahalanobis distance for those just tuning in. It's like typical Euclidean distance, the distance between 2 points on a grid, except you account for understanding that those x and y coordinates are perhaps not totally independent. That you're no longer on a physical plane, you just have some arbitrary variables and you're computing the distance on them, and you know, well, I know that variable 1 and variable 2 are very similar, so I shouldn't count that full distance. And so you've got this correlation, the covariance matrix, excuse me, to account for those correlations. Otherwise, it's very similar. If your variables all happen to be independent, it works out to the same thing as standard Euclidean distance. So, we successfully implemented this last time. Woohoo, there we go. Oh, the bold M's are the bad ones. I had these M's in this font. When it's huge, they just look like little floppy disks, but it's the bold ones, that's why. Whereas the regular M's are totally fine. Anyway. Okay. So we have our Mahalanobis distance stuff left over from last time. Let's start up our IPython session. Yes, we have to source our virtual environment first, and then it lets us know we're in that virtual environment, which is nice. Bust up some IPython, and there we go. Just as a reminder, let's remind ourselves what the heck it is we're doing here. So to do that, let's just reload some of this data. There we go. And because, let's turn off the auto indentation so our slime muxing doesn't get screwed up. Okay, so I'm just going to do a quick recap. We're importing all the stuff we need over here. We are going to initialize our data over here. We're going to have 100 observations, 2 variables. Data is just an array of the observations of variables. That's where we're going to store them. Then we're filling it up with some 2 very correlated variables. The first variable is a random number between 0 and, it's a random number, 0 or 1. The second one is a random number that will be 50 times the first number plus a random integer 0 through 50. So at most 100. So let's do that. Bing, and there's data. And you can get a sense, okay, the first column, yes, that's all zeros and ones. The second column, that's digits, there's a 0 in fact. Did not expect that. And there's 99. In fact, I bet if we say numpy.max data, we happen to have the largest value of 98. It could have been bigger though. Okay, super convenient thing. Numpy can compute the covariance of our little data set, the covariance matrix of our data set. We just have to tell it that this row variable is 0. That says that each row is sort of an observation, and the different columns mark our different variables. So that keeps it pretty simple. Let's do that. And we have to turn it into a matrix object in NumPy, not just an array. The type of V is an array, but the type of VM, our matrix, is numpy.matrixlib. And that's so that we can do this inverse thing, vm.I, as opposed to just VM. Because we need the inverse in this formulation to compute the Mahalanobis distance. Okay, let's pick a data point. Or, no, sorry. X and Y is just telling us which. Yeah, no, those are our 2 data points. I confused myself. X is the first data point, Y is the second data point. So if you wanted to compute the Euclidean distance here, you would say that's 1 squared plus What's 81 minus 13? I ought to know that. Boom, 68, okay. Plus 68 squared. Most of the length is in 68 squared, you'll notice. Plus 1. And numpy dot square root. So, wow, yeah, go figure. The Euclidean distance is about 68. So that's interesting. This is the function we wrote to implement Mahalanobis distance in NumPy. Again, that's in NumPy. So we can see that now with x and y, and we throw in Vm because that's the covariance matrix. That gives us this 2.32. So that's a very different distance from the Euclidean distance because these are such highly correlated variables. All right. Then I'm gonna use the Mahalanobis. No, I'm gonna use the TensorFlow implementation. That's over here. Again, we've got our number of variables right here, which is just how the two columns of x, which is the two variables, the really small digit and the big digit. Then we open up our TensorFlow session. The session is what's going to actually run the graph that we're going to set up. The graph is what's telling TensorFlow how to compute the Mahalanobis distance. So to set up the graph, we set up this placeholder variable for the first data point and for the second data point. So I've called that XX and YY. I'm using float 32s. It could be whatever. It's essentially an array that's num_vars long, which in this case is 2. And this VI, because I was on this doubling theme, that's the inverse of the matrix. Hence, I'm passing that in here. This is what we're going to try to fix up today. We'll take the inverse inside TensorFlow. So that should be good. Again, that's just a placeholder. That's a sort of a way of implying to TensorFlow that this is going to be a variable I'm going to input things to. Diff. This is just the subtraction, that first step, because we need to use that value multiple times, this x minus y. So it's an array subtraction. And again, when we call this line diff, we are not actually computing anything. That just creates the node for TensorFlow so it knows, hey, this is what I need to use to actually compute it later. Again, following the formula, we need to take the transpose of this function and of the difference, and we also need the difference itself. We have to use Reshape here to get it into a proper array of the style that we want. It's still essentially one long. It's basically a vector, but it's to do our matrix multiplication. We have to compute this properly. We do the left multiply first, so the transpose times the V inverse, and then we have that bang into the right-hand side. Do the other multiply. We take TensorFlow at square root. That's built in. It takes the square root of our matrix, which is really convenient. Ends up just being a scalar. And this output is that's the final node of our graph. And then we tell it to run. We have session.run. This is what our output is, and this we could ask for other things too. We could ask for M2 or whatever. We can get that out too and see what it looks like. I'm not particularly interested in that right now. Feed dict is the inputs. So what's going to go into variable XX? Well, we're going to put X. What's going to go into variable YY? Well, it's going to be Y. What's going to go into variable VI? It's going to be VI. So this gives us some actual value. And then it returns. So that opens up a session using the with tf.session as sesh. And then creates the graph, runs the graph, and finally goes. All right. So let's just double check for ourselves. X, Y, vm.I. Remember, we have to pass in the inverse here. That's something we're going to fix up today. And you see we get the same answer. 2.32, 2.32. There's some numerical precision differences. I'm not worried about that. Depending on your application, that might be a problem. That might be something you have to worry about. All right, so let's let's try to change this now. I would like to, instead of passing in this VI, the inverse of the matrix, I just want to pass it in V. And so I'm going to change this to V and V. I'm going to say VI instead equals TF dot inverse. I saw this last week. TensorFlow matrix inverse. I definitely saw this last week and I don't remember. Matrix inverse is slow compared to, oh, that's interesting. That's not really what I wanted to see though. There was a, no, that's not what I want. It was on the TensorFlow website. They've got like a super good, is it this one? Oh, this is source code. That is not what I wanted to see. No, that's, if you're looking at source code, you're desperate. You're sort of at the last recourse. Is it in here? Dot matrix inverse? What does that tell me about this? Calculates the inverse of a square invertible matrix. Checks for invertibility. Alright, well that'll work. Matrix inverse of VV. Yes, and VV is of type float32 VM, excuse me. We could probably pass in V or VM in this case, since TensorFlow will convert it into a matrix, I believe. Let's double check that. Calculates inverse of square invertible matrix. Input a tensor, right. Must be of type float32, float64. Shape is M by M. Okay. So that's convenient. So I could just pass in the numpy array, and I don't have to pass in the numpy matrix. It should work with both. We're going to find out. Okay, that should be all we have to do, actually. I probably could have done this last week, but I just barely cut through it in a little over an hour, so let's redefine our function. And let's say, yeah, x, y, and let's pass in VM first. Be more conservative. VI is not defined. Right. VI is just V now. That's things only work on the first try about 1 out of 100 times. It's those times are nice. I like to enjoy those times. Okay, that is a different answer. So that's wrong. I've done something very wrong here. That's cute. So let's take a look at VI and see what the difference is here. Conveniently, we can look at that. Get the output as well. So now we're going to be outputting what we believe to be the Mahalanobis distance, which is wrong, and something else as well. Because I redefined VI. Invalid argument. Matrix inverse 2 is both fed and fetched. Oh. Therein lies the problem. I'm trying to input into VI, which it will let you do. The program is only too happy. TensorFlow is only too happy to let you input into an arbitrary node or variable, which is useful, because sometimes, for debugging purposes especially, you want to do that. You want to just get in there directly. Or maybe you've pre-computed something this one time and you want to see what happens. Okay, now we're getting the correct result. This is 2.32. So I don't need to do that anymore. Okay. Let's redefine this again. Just to verify to ourselves. Yes. Okay. So now we are in fact passing in just the base array, just like we are over here with the Mahalanobis distance. In fact, oh, that's not what I want to do. Let's try our timeIt function again. So timeIt, if you might recall, is a numpy pm.I. What? That's weird. TimeIt is a function that will run your function many, many times and give you the sort of best result. So here it said I tried 10,000 loops. The best of 3 is 65 microseconds. So that's reasonably quick. And the TF implementation now, it's probably not going to be that good. I'm guessing 65 milliseconds or so. Yeah, 104 milliseconds. It only did 10 loops, you'll note. Things that take longer, it does fewer, because it doesn't want to make you wait too long, which I understand. So yeah, again, it's that factor of 1,000 slower because we're framing a problem that is not well posed for TensorFlow. We've got a very small dimension. There's not a lot of parallelization it can do in the background. If we had maybe many more dimensions, if we had our nodes going off in several directions and then coming back together, maybe that would make sense. Okay, that was easy. That was easier than I was expecting. So that's good. Next, I want to have TensorFlow compute the covariance matrix too. So I just want to say, given the data set, then here's the data set, boom. Let's say, give me the distance of every guy to the mean. That's a common thing that you'll see in Mahalanobis distance, in any distance metric. You'll see that here. I believe that's this. What the heck is SI here? SI is the variance of xi and yi over the sample data set. Oh, no, sorry, I'm looking up here. This is the Mahalanobis distance for a point from the mean of a given data set. So we can sort of compute this for every point to see how far it is from the, I'm going to use the quotes, center. It's not a mathematical center, just the mean data point. Depending on your data, it might not be near anything, but that's okay. All right. So what do we need to do? We need to compute the actual covariance matrix. That's what I was getting at. So let's see how we can do that in TensorFlow. If there's a built-in, that would save us a whole lot of effort. Covariance matrix. Can we do this? Least squares, again, looking at source code is not what I want to be doing. Oh, maybe not. This could get tough. We might have to compute our own. It's not the worst thing in the world. Got to compute our own covariance matrix. But it's probably going to be inefficient because I'm doing it on the fly here in an hour, and that's probably going to consume most of my time. Yeah, okay. Images. This is like the API setting that I was using before. So covariance. Here we go. Per image whitening. That's definitely not what I want. This is what I want? Here we go. Let's try. Really? No covariance? Python API? No. Dang. Only one on COV even. Alright, we might have to implement this ourselves. Alright, we're gonna do it. We're gonna see how bad it goes. Okay. Okay, if the entries of the column vector are random variables, each with finite variance. Oh gosh. So now I have to remember how the heck to do this. You would think, like, having gone to school and learned many things, I would have remembered this. Constant matrix, the inverse covariance matrix, precision. All right, Wikipedia, you are not helping me. Covariance matrix, data sets. All right, stat track. We will try you. I don't normally check it out. How to construct this covariance matrix. We will check this out too. So if given a covariance matrix, I can find the eigenvalues, move forward from there. blah, blah, blah. This guy's asking how to construct the covariance matrix. The variance of individual variables, and then the covariance of that particular variable. Okay, so covariance is apparently 1 over n minus 1 times xi minus its mean times yi minus its mean. Is that true? Is that what we get here? Why do these guys have n and they have x minus 1? Number of scored. I mean, that's not going to make a big deal. But I would have liked to have it correct. Conflicting nomenclatures, block matrices, estimation. Strictly speaking, I don't have a full population, I just have a sample data set. The column means were known a priori. They are not. They are estimated from the data. Okay. So if you happen to know something about your data set, that a particular variable has a definite mean regardless. Oh no, is my stream stuck? Let me try pausing. Okay. I think we're back. Sorry about that. Sorry. Don't know why Google choked on me there. And now, of course, now it's like 30 seconds behind wherever I was. Okay. I believe we are now back. Life is good. So what was I saying? Yes, if you happen to know that a particular variable has this particular mean, not just based on the given sample set that you have, like some historical information. The sort of classic example is if you run a factory and you make widgets and you have measured every widget you have ever made, and so you have a particular population of widgets, and you know the length of the widgets is always this certain number. So you've got a set of length measurements. You know what the actual mean of all those is. So you can use this sort of slightly, you know the column means a priori. So then you're going to do this 1 over n times this other business. But if you don't, maybe you only, I made a survey and I got a bunch of people's information, maybe 1,000 people out of some much larger population of a city. And I got their mean income or something, say. Well, then I'm estimating the mean of the whole population of the whole city based on just this small sample. And so you're going to use this other data. You're going to use this other formulation. You'll notice, like, if your n is huge, it's not really going to make a big difference. 1 over n versus 1 over n minus 1. So as your sample size gets larger and larger and larger, you become more and more confident that the mean of your sample size is very close to the mean of your actual population. We're only using 100 data points in our mystical sample. We'll do the 1 over n minus 1 because that's nominally appropriate. Never mind, we have totally fictitious data anyway. So this Stack Overflow thing is what we want, I believe. Let me... Yes. N, X, I, Y. Yes. So we got to compute the variance of every variable, and we got to compute the covariance of each variable with every other variable. So we got sort of n things to do on the diagonal, plus like n squared things, sort of n squared over 2 things to do on the off diagonals. So here's what I'm going to do. I'm going to implement it outside of TensorFlow first, and then I'm going to sort of translate it in, because that way I don't have to think about the placeholder variables and all that stuff and using the special syntax. Let's just call this Cove, and we have our data set data. Am I smashing my namespace? Yeah, maybe. We are going to compute covariance matrix of data, and we will say each row is an observation. Each column is a variable. Yes, in the NumPy covariance, you can tell it which axis you want to be what. But this is just a roll your own thing to learn, so we're not going to worry about that too much. So let's just start doing this the naive way, and then we'll slowly optimize it as we go along. When you're doing kind of exploratory data analysis, I often find it's better to just push ahead and try something, and if you find that's what your bottleneck slowing you down, go back later and fix that up. Trying to optimize too early just gets you stuck and you don't get anywhere. But it's still really hard to not do. Okay. So number of variables, let's say num obs comma num bars equals data.shape. Data being this, and I say data.shape. Data.shape is an attribute, not a function, but not a method, of course. So that'll store 100 in numobs and 2 in numvars. Okay. Then I need to walk through. This is kind of bad. I want to walk through what? Every observation? No, I need to walk through every pair of variables. So sort of for v in range numbars. This is super unpythonic. Will work with me. Oh no! First we need to compute the dang means, don't we? Yeah. Silly. So let's make a matrix means or a list, whatever. numpy.mean, I believe you can just give it an axis. Yeah. numpy.mean of data. Of course, that computes the mean over all things. That looks about right. It should be about half and about. Honestly, would have expected this to be. Oh, so I guess it's. Yeah, it should be like 25 plus 25. So that's about right. All right, so means, we'll just say for the moment numpy.means of data. Again, that's something we'll have to fix up, but that's okay. All right, so for this variable, what are we computing here? I need the difference of every observation against its mean. All right, so diffs equals, I'm gonna use a list comprehension at this particular instance because I'm a terrible person, and that's okay. No, I'm not actually. I'm not gonna do that. numpy.copy. No. What am I gonna do here? Yeah, let's copy this. Data minus means? What happens? Oh, means is not defined. Oh. It's called mean, not means. So I'm trying to see, does this do the expected thing? Oh man, it does. I love America. Wait, I don't think that, did that work? Yeah, that worked. So NumPy did the right thing. This is like magic. NumPy says, you've got this big matrix, data, minus this small, or you've got this big array, data, minus this small array, means. but their shapes match up in this direction. So I've subtracted the first thing from the first column, the second thing from the second column. That's brilliant. That's dark sorcery is what that is. So that's beautiful, because then I can just say data minus means. And I will wonder if the same thing will work in TensorFlow. We're going to find out later. Okay. Then, for each of our variables, what do I need to do for v in variables? For v1 in variables, for v2 in range, v1 comma numbers. And that's when I say, right, COV equals 0, start off at 0, COV plus equals diffs, hang on. Diffs of v1, that's variable 1 that I'm working with. Oh, I know I only have 2 variables here. So that's cheating. Like, I want this to be mildly generic so I can have an arbitrary number of variables, as opposed to just saying like this. So I know that there's 2 variables. That's this section right here. And I'm going to add up and then multiply it by this number. But here I'm cheating. I'm saying, I know that there's only 2 variables. So that's not really right. Import iter tools. Iter tools combinations. There we go. That's going to be what I want. I want all combinations with replacement because I have to have variables against themselves. That's going to be just the variance. But you'll notice it's the same computation, which is nice. With replacement, how does that work? Given some iterables, such as, I don't know, diffs, say. How many do I want? 2. I want all pairs. Diffs is not defined because I never actually clicked that apparently. Ding. Let's do an actual list. How long was that thing? 5050. For those of you who don't know, the sum of all numbers 1 to 100 is 5050. That's a fun trick to occupy grade schoolers for a while. Any of them who are budding mathematicians will solve that pretty quick. That's interesting. Did I do this right though is the other question, of course. Diffs, what is diffs again? Diffs, right. Right. I want, what do I want? No, I want all the columns of diffs. Right? No. No, that's not it. Oh boy, oh boy, oh boy. This is all pairs. That's not right. I want all pairs of variables. And then the sum of all diffs. So diffs isn't right. But I could say range 2, 3, 2, 2, 2. 0, 0, 0, 1, 1, 1. So I could do it that way. I feel like there's probably a better way, but that's okay. So iter tools dot combinations with replacements range 2. Range not 2, range num bars. There we go. Comma 2. Yes, because it's every pair of variables that has to have something happen. And what is this? For v1 comma v2 in I say covariance. All right. Now I'll make the whole dang matrix right here. numpy.zeros, numvar. So the size of our covariance matrix is numvars and numvars. Okay. So covariance of v1, v2, those are just the indices to my variables, equals, this is where I need this function. So, sorry, v1, that tells me what variables I'm working on. So I need to take a given variable number and sum up for every, suppose v1 equals 0 and v2 equals 1. So I'm on the off diagonal then in this fictitious universe. Okay. That's v1, that's v2. I need a drink. Got my delicious water here. Just need to stop and like think for half a second. You think this wouldn't be that hard? So essentially, I've got my diffs, right? Yeah. So really, I just need d, need to multiply d of v1 times d of v2 for d in diffs, and sum that up. All right. So then the operative question, these aren't squared, right? No, they're not. Can I do this as diffs of v1? No. Diffs of everything, comma v1. Yes. Times diffs of everything, comma v2. And sum of that. There we go. Because again, we're working with pairs of variables. And this will do the element-wise multiplication. There we go. And I'm going to go ahead and say numpy.sum of this. Again, another thing in TensorFlow that we will have to implement ourselves. I'm now thinking I'm not going to finish that, but that's okay. That doesn't matter. Yes. And that should be good. And this also needs to be true. There's a very minor inefficiency when v1 equals v2. We'll be doing this computation twice. Actually, I don't need to do the computation twice. I just need to copy that value over there. Right. That should save myself a little bit of time. All right, so I think that's the covariance matrix. Now we're going to find out what I did wrong, as usual. Okay, those things aren't right at all. Oh boy, what did I do wrong here? What did I do wrong? Oh, I forgot to multiply, first of all. Forgot this important step. That's dumb. 1 divided by n being, what is that? N is num obs minus 1 times. So I had the wrong size data, clearly, I think. Do I? I thought the covariance level to which two variables vary together. Estimate the covariance matrix giving data and weights. Array like 1D or 2D array containing multiple variables and observations. Ugh, gosh, did I do this whole thing wrong last week? Just when I thought I was doing well. Just when I thought I was doing well. Covariance matrix of the variables. Oh, no. Hang on. Rho var equals 0. Yes, so I just need to compare the V. So V versus my computation covariance of the data. So you'll notice the scale of the numbers is pretty close, right? That looks right. Except, oh, my scientific notation, these are way the heck off because I didn't have I missed my my multiplication there. So that was as though you had 2 observations. So yeah, the covariance is much larger in that case because you have much less confidence in your data. V0 is not defined. That's because V0 does not exist. How did I change that? V1. Boom, covariance zeros everywhere. That's cute. Alright, so let us see what went wrong here. That's what we should get. This shouldn't be rocket science here. Num obs. Minus 1 is, of course, 99. That's not too bad. What's V1? What's V2? Let us suppose that those are what they are. I did not actually want to run that whole line. I wanted to do this. Interesting. My Slimux appears to no longer be working correctly. It's sending a line rather than the individual component. Let's look at that later. So that's 0, supposedly. See? Oh, I'm getting burned by Python 2. Getting burned by Python 2, man. Oh, hell. 1 divided by 99 is 0. 1 div 99, 0. Alright, so I essentially had to cast this to a float. Because 1 divided by 99 dot... Oh, well that's a number. Yeah, totally. That's one thing I like more about Python 3. Yeah, and I know when I was looking at the TensorFlow GitHub page, the issue for converting to Python 3, and double checking all the division is one of the things they had to do. That's just a pain. Okay, let's see what we get now. Hey, what do you know? Those two things, in fact, look equivalent. Are they actually equivalent? There's some numerical and precision errors, but I'm not worried about that. Okay, so we have a covariance function. We have a function to compute covariance. And that's just using NumPy. Good for us, good for us. We got somewhere, something got accomplished tonight. Let's see if I can do, let's start simple. Let's see if I can do just this covariance function in TensorFlow. Nothing else. I only want data, some kind of array coming on. Compute covariance. Whoa, I need space. Matrix of data in TensorFlow. So naturally, like anything, I have to go see and ask, how did I do this before? Because I can never remember. All right, so I do think outside of TensorFlow, I need to pull my, for the moment, I'm going to pull my shape, the number of observations, the number of variables outside of TensorFlow. Whoa, but of course I don't want that before there. All right. Num obs, comma, num vars. So this is our data. I'm gonna call this DD because why not? And so now I'm gonna walk through my covariance function and just start translating things and see what happens. You know, because that's, again, I'm just defining the graph. That's all it is. Nothing too fancy. Sorry about that. Okay. Also, it helps if I could spell covariance properly. Actually, it doesn't matter. All right, so I need to compute the mean of each column. So I want to see, like, I know how to do that. I can literally add those up and divide by the number that I have. But I want to see if TensorFlow has a built-in function for that. TensorFlow mean. Yeah. Mean for AI. That's... I feel like this is an ill-formed question. It is yet another software tool. What does it mean to have TensorFlow? Oh my gosh. Like, I really don't want to search for average because I don't think it's going to be called average. Why is it performing so poorly? Probably because people have not optimized how they're programming in it. Ugh. Storage APIs? That's not what I want. This is what I want? That's not what I want. API. Python API. Here we go. Mean. Random normal. Go through all the randomization functions. Reduce mean. That looks like it might be a winner. Computes the mean of elements across dimensions of a tensor. That's exactly what we want. So we're going to put our tensor input data. Reduction indices. What are those? Keep dims. What are those? Let's find out. Along dimensions given in reduction indices. This is sort of like the axis command in NumPy. Unless keep dims is true, the rank of the tensor is reduced by 1 for each entry in reduction indices. Right. So if you're computing down the columns, you want to have 2 numbers left. But if for some reason you didn't reduce, if keep dims is true, the reduced dimensions are retained with length 1. That's kind of weird. So do we have an example of that? Reduce all? All right. All right, so let's do that. I can just copy that, which is convenient. Bam. Reduction indices. We're gonna find out if this is the same axis styling as NumPy. I feel like it's the opposite. So we're gonna find out. Sesh, is Sesh a thing? Sesh is not a thing. TF interactive session. Again, we'll place your bets now to guess if I remember to close that session or not at the end of this. I'm betting not. All right, tf.reduce mean. And this is gonna be means. As before, again, we sort of sketched it out in standard Python. And now we're just translating that to TensorFlow. I find it's often a lot easier, especially when I'm learning a software library, to write whatever I want to do in something I know, even if it's just on paper in pseudocode, and then write it. It just, writing it in once forces me to logically think through things. All right, now I've got the diffs. So this is going to be a little interesting. Here, all we did was simple subtractions. I know that TensorFlow has subtraction. I don't know that this is going to work correctly. So we're going to find out about that. We can do tf.sub. What I'm actually going to do here is I'm going to define this and my means, not input tensor, no. Thank you for yelling at me. Thank you, Python. That is actually helpful. Okay, that's the means. Those are my diffs. And then I'm going to say diffs.eval. Can I pass in feed dict? Yes. So I need to say dd is data. That's the input I'm passing in. And then the question of the hand is, oh crap, I got rid of my old diffs. Okay, but that looks approximately correct, right? Yeah. Again, I've got 50.509999 instead of 0.51. But that looks like it has actually done the correct thing. So that's cool. The same magic, the same sorcery from NumPy is in TensorFlow. So cool. Of course, we'll find out if I'm doing this all wrong when I try to do it in the Mahalanobis distance again. That was reduced mean. What's the next thing? So we just keep on going. This is like literally line by line. This is not a place. This is a tf.variable, tf.constant. What do I want to do with this here? So the question is like, well, how do I... This loop can totally be parallelized. Like, it's 100%. These are embarrassingly parallel. Like, you have memory accesses and the same things. That's the only thing slowing you down. So what is the best way to do that is a good question. Let's go tutorials. Let's see if there's something I missed. I don't want the deep MNIST. No. Mechanics? Maybe just mechanics. No, that's not even... Is there a for? Is there a for loop? For. I feel like if I write a for loop, I'm doing it wrong in TensorFlow. I ought to be able to have... well, yeah, except for the final loop. And for loop that accesses basic RNN. I don't even know what that is. Oh, Teano. Yeah, I'll check that out at some point. Yeah, this doesn't seem like the right kind of thing. Get shape, edge shape. Oh my gosh. Yeah, note that the solution, no for loops. People on Reddit are posting about TensorFlow. Maybe I should, does it have a, it's in machine learning. Yes, I posted one of these videos to there. Got 0 upvotes. I should not be surprised. I may be cutting short this video before implementing this final part, but that's okay. Because not everything, this isn't really about TensorFlow. I'm just using TensorFlow as something new that we're all still learning about, just to show how I'm learning. Where? Oh, you know what? We can do this the stupid way first, and then I can worry about it. That's always the thing I like to do. Do it stupid, and then I'll figure it out later. And like eventually we worked our way out to something that wasn't insanely stupid over here, but probably a little slow. That's why I try to use built-ins whenever possible. You know what? Let's do the stupidest thing. And also, let's tab new. This is from the MNIST data. I just opened a different file. Just trying to see how do we go about doing this. Just reduce sum. That's what I need. Some kind of reduce. Oh boy, lots of things open. Ooh, TensorFlow. Reduce sum. No, not that. I just want the... I really need to just bookmark that one page. TensorFlow API. That's really what I want. Yes. Hello. Thank you. Python. Reduce sum. There we go. This is probably something what I want. So this is going to go over, do something to every dimension of a tensor. Is that really what I want? I've got, again, I need this all pairs of variables. So do I need a node for every pair? And I want to do this to that node? This is an interesting question that I haven't really run up against in TensorFlow. Reduce mean. Oh, is there a freaking reduce mean function? Use the mean of elements across dimensions. Oh, I used that before, didn't I? I swear, I'm like a goldfish. I got this 10-second memory. As soon as I forget. Don't ask me anything about last week's videos. Clearly, I have already forgotten. Accumulate n. Turns element-wise sum of list of tensors. That's a good idea. Segmentation. Use to perform common math computations on tensor segments. What about TensorFlow? For loop was way too generic. Pairs of columns. That might not really be what I want. We're predicting a column. No, that's not right. I'm gonna have to stop and like probably think about this. This isn't something I can just talk myself out of, essentially. Oh, now I feel like an idiot. Again, I could do it with the for loop. That wouldn't be terribly hard. I just feel like that's the wrong approach here, and it's worth spending some time to think about. Sequence comparison and indexing, sparse segment. Maybe TensorFlow combinations? Performance benchmarks, that's not what I want. Does TensorFlow have its own Reddit? What? Oh, I'm gonna start posting to that. Alright, I'm gonna be posting videos to TensorFlow Reddit from now on. Even though it's got 118 readers. Well, less competition, right? Cafe, TensorFlow, unites research and production, fatal error and something. The white paper. My video. It's always fun to see my own video. I guess that was November 9th. I was right on the money. I feel like I must be missing something here. Right, because I've got one operation that I want to do a whole bunch of times. But I need to do it in this like n squared number of times. So if I said what is this going to be? This is 1 over float num obs minus 1, all that times not numpy.sum tf.reduce of what? Of something like some kind of input and then some kind of output, or some kind of input. And I need to define what all those inputs are. Again, how did this work over here? How did I say this goes into that? Here, I've got this 10 long vector, another 10 long vector, simple matrix equation. Maybe that's what I need to be thinking. No, but that's like the fundamentally different thing. Either I do, yeah. All right. I will ponder this because I don't wish to just have a for loop in the middle of my TensorFlow operation. And this is a set that can very easily be parallelized away. So that is what I would like to happen. And I know I've done this before, but it's new in TensorFlow, so there's always a barrier to come up against. So I think I'm going to call it there. And I'm going to have to think about that real hard next week. Maybe I'll figure it out. So we didn't get into that much TensorFlow stuff today. But we did some. We ran over some of this. We computed the matrix inverse on our own. That ended up being super easy. There's a function for it. Huzzah. And we started writing our own covariance matrix routine. again, we don't have to do this kind of thing. Like computing the covariance matrix, that might be something that you just want to do, and you would do that with NumPy, for example. So maybe like before I could modify this to accept just the data and use the NumPy covariance matrix calculation, or even my own hand ruled routine. For fun, let's see how bad my routine is, my covariance matrix routine is, compared to NumPy. It'll be the last thing we do in this video. Mine takes 46 microseconds, which is honestly better than I thought it was going to take. NumPy, however, NumPy's probably 105. Look at that, I'm faster than NumPy. No, it's probably that NumPy is optimized for slightly larger arrays, whereas we're working with very, very small arrays right now, and that's why it's not taking very long. So, but maybe it's not too terrible is what the implementation is telling us. Oh, I switched over to the, I'm really sorry. I switched over to the break a little too soon. So you can see mine, 46, NumPy, 105. Sorry about that. All right, I will see you all next week then. And I think probably the week after that is between Christmas and New Year's. I will probably be off. Until then, keep looking at data.